let me press record. Good to see you again. It's week 9, Thursday afternoon here in Sydney. How is your week going? Who has finished lab test 2? Let me know how it went in the comment section. So, yeah, how did it go? Let me know. I think most people found it pretty predictable. I don't know, what are your thoughts? So as you know, today is a tutor-led tutorial. So Brendan saying fine, Cynthia pretty well, and Liz says good, and Isabella said pretty well as well. So great. Thin, silly mistake, don't worry, these things happen. So in this tutorial, we will look at linear systems. It's an algebra tutorial. And so I'll just be stepping you through some of these questions. Now, it's been a bit of a difficult week for me. I actually had to take some leave earlier this week because I was pretty ill, and I'm not feeling great today. So please just be gentle with me today, okay? So let me share my screen and we can have a look at some questions. All right, so this is from the algebra course pack, chapter 4. Now, in previous tutorials, I did some of the earlier questions. So in this tutorial, I'm hoping to do some more of some different questions, okay? So I thought we could start at using linear matrices to write linear systems. Here in this question, we're asked to find the solutions and give a geometric interpretation of the solution. So I did A in the previous tutorial, but today I think I'm going to do B. So we've got 3 equations and 4 unknowns. So the way we would write this is just to look at the coefficients and write them all down as an augmented matrix. So let me share my screen with you and we can look at what's happening on my document camera. Okay, so this is question 13b. Let me just change that a bit. No, that's okay. All right. Let me turn that down a bit and that up a bit. There, that's better. All right. So in this question, we can write everything as a augmented matrix. So this is the first row with the coefficients of each variable, and then the right-hand side. Oh, sorry, hang on, I put them in the wrong spot. So this is a good lesson to make sure that you are carefully, so that's a 2 there, you are carefully transcribing this. So that's a 2. Oh, yeah. Okay. All right. So when we use these matrix forms for our linear systems, what we would like to do is make this as simple as possible and as easy to deal with as possible. Now, if you look at the form of this matrix and you look at each row, you come across these leading entries, right? So you've got zeros, zeros, and the first non-zero term is called your leading entry. Or of each row. Okay, so you can see the first column has a leading entry, the second column has a leading entry, the third column has a leading entry, the fourth column does not have a leading entry, and the final column does not have a leading entry. Okay, so believe it or not, you can actually say a lot about your solutions just by doing this kind of analysis. Okay, now before we go and solve this, let's actually make it a bit simpler. Can anybody suggest some basic row operations to do on maybe row 2 and row 3 to make things a bit simpler? You can suggest something in the chat. I don't have to do them because this is already in row echelon form, but can anyone suggest what we might do? So Isabella's saying divide everything in row 2 by 2, and Cynthia's saying divide by the common factors. Yeah, I think we can take out these common factors of 2 here and the common factors of 7 or -7 there. So what I would do, and you don't have to do this, right? I'm just trying to show you that. So I guess we can capture it as that. And then I guess row 3 is going to become, I guess you can take out the -7 each term there. And now it's not necessary, but it can help with the calculations. Make it nice and simple. So we should get something like that. Okay, so that's still in row echelon form, and the important thing now is that is a non-leading column. Okay, so I'm going to introduce a parameter to be this column's variable, right? So this is the x1 column, this is the x2 column, x3 column, x4 column. So I would let x4 be something like lambda. Okay, move that down. And so what I can do then is work with each row and use back substitution. So row 3 says x3 minus 2x4 equals -2. So I can use that if I just rearrange it to get this. Okay, and so I know that I've let lambda be x4, so I can just come up with this. So I've expressed x3 in terms of this parameter. Okay, so we've done that row. Let's go next to row 2. So that says 2x2 plus x3 minus 2x4 equals 4. So we can write it like this. And we will just substitute this in for x3 and this in for x4. So I'm going to get something like this. And now we just simplify it, right? So 4 minus 2, that's 6. negative 2 lambda plus 2 lambda is just 0. So x2 is just a constant in this case. And finally, from row 1, we're going to get 3x1 equals 10 minus 2x2 minus x3 minus x4. So all we need to do now is put these things in for x2, x3, and x4. Okay, so what are we going to get there? We're going to get 4 plus 2, which is 6, and negative 2 lambda minus lambda, which would be negative 3 lambda. So x1 is going to be 2 minus lambda. Okay. So we've got x1, x2, x3, x4. The last part of this question is, if possible, give a geometric interpretation of the solution. Who can tell me what is the geometric interpretation of this solution? Can anyone tell me in the chat? Thing says a line. Why is it a line? You're on the right track. What tells you it's a line? Right. One parameter equals one dimension, and a line is one dimension. Okay? So the solution set is a line. Okay? And if you wanted to write it out, it would be something like this. Oh, I probably won't fit this in. Let me see if I can fit this in. Oh, I'm not going to fit it in. That's x4, believe it or not. Let me see if I can make this a bit neater. Okay, and here, lambda is from the whole set of real numbers. That's my squished little solution. Hopefully you can see it. Yeah, Brendan, absolutely correct. It is the parametric vector form of a line. Lambda is the parameter here. So you described it perfectly. Okay? So I've kind of squished my solution in there. You don't need to do that. You can take more space if you want to. All right, so let me scroll down a bit and we can have a look at, oh yeah. So let me go back here, back to my PDF. All right, now these kind of problems are classic Math 113 problems. For each of the following linear systems, find x1, x2, x3 in terms of b1, b2, b3. Now, the thing is, you don't know what b1, b2, and b3 are, okay? And their values will tend to influence the solution set, or like they'll usually have some effect on, you know, what the solution is or whether a solution even exists. So let's unpack this one. I'm going to do part B. All right, so 3 equations, 3 unknowns. So let's transfer that into the augmented matrix form, and we can do some analysis. Okay, so let me go back to my document camera. Okay, so consider please our augmented matrix form. And we need to be really careful that we put everything in the right place, because if you switch the columns, you're in trouble, okay? Okay, so we're going to consider that. Okay, so can anyone suggest what our first row operation would be? This is not in row echelon form. Can anyone suggest on the chat what might be our first row operation? Who can tell me? Row 2, modify row 2. Brendan. So how would you do that, Brendan? Row 3. Let me know what. So row 3 becomes row 3 plus 2 row 1. Yeah, that's all right. Keep them coming, people. Keep the suggestions coming. My first suggestion, yeah, Nace's right, Isabella's right. I would like to even make something, before we do any adding or subtracting, I would actually just simplify row 1. So we have a number 1 there. And then we can do the row operations. Okay, so if I was doing this myself, I would go, okay, row 1 is going to become a half times row 1. Yeah, Liz is on the case. Now you don't have to do that, but the nice thing is you get a 1 as your pivot entry point, right? Now you might go, well, Chris, you've got a half B1 there, which is a bit ugly, but we can deal with it. Okay, so this is going to be my pivot entry point. And what I would want to do now is make everything in the column below that equal to 0. So now let's use your suggestions. Row 2 is going to become row 2 minus 3 row 1. And row 3 is going to become row 3 plus 2 row 1. Okay, because that will force that to become 0, and that will force that to become 0. So let's see what we have here. So I'm going to get 1, 0, 0. Row 1 does not change. We haven't done anything to row 1. Okay, and now that's a 0. So that's not going to affect this or this. Okay, so row 2 minus 3 row 1. So that minus negative 6. So it's going to be negative 2 plus 6, which is 4. Okay, row 3 plus 2 row 1. So negative 1 plus 2 times negative 2. So that's negative 1 minus 4, which is negative 4. So up here, we're going to get B2 minus that. And down here, we're going to get B3 plus 2 times a half B1, which is just B1. Okay. So hopefully you can see now that row 2 and row 3, these elements are just, negative 5, thanks. Thank you, Ningxia. Got to make sure we do our calculations correctly. Okay, so hopefully now what you can see is, right, I'm now going to work on this. So forget about that. This is my new augmented matrix, and I'm going to row reduce that. Okay, so I go up here and I say, oh, that's going to be my pivot point. So this is going to be my pivot, and it's already equal to 1. So that's good. So what should my next operation be, everyone? I want to make that into a 0. What should I do? I've forgotten. I'm so sick. I've been so sick this week. I have forgotten how to do row reduction and Gaussian elimination. Yeah, row 3. Thank you, Cynthia and George. Row 3 becomes row 3 plus row 2. Okay, so we're not changing anything to do with row 2. Row 3 is where we're going to see the change. Okay, so that's 0. That's going to be 0. This will be -1, and we're adding this to this. So it'll be B3 plus B2 minus a half B1. Okay. So now this is in a row echelon form. So that's a nice form because we can make some conclusions now about the solutions. All right, so we've got a mess over here, but that doesn't matter. This says negative, this is the x3 column, yeah? So negative x3 equals that. So we know what x3 is immediately. Then we can back substitute to get x2 and back substitute to get x1. So from row 3, it is x3 equals this. Okay. Row 2 says, oh, well, it's x2 plus 4x3 equals that. So x2 will equal okay, so to work this out, you just take that and put it in there and simplify. And then row 1 says x1 equals this plus 2x3. Okay, so you know that can go there, that can go there, and then you just need to simplify. Okay, so I'll leave those last steps for you to do. Now, a couple of things before I move on to the next question. Let's look at our row echelon form. Okay, there's the leading entry for row 1. There's the leading entry for row 2. Here's the leading entry for row 3. So if we look carefully, that column's a leading column, that column's a leading column, and that column's a leading column because they each have one leading entry from each row. So all of these left-hand columns are leading. That means there has to be a unique solution. Let me say that again. When all the left-hand columns are leading, right, it means you have the system has a unique solution for every B1, B2, and B3. All right, Tom has a good question on the chat. Should we change it to reduced row echelon before we work with the equations, or is that too risky? Tom, I guess it depends what works for you. In this like it depends where you want to do these substitutions. You can do them up here when you go back up and make that 0, or you can put them in here. It just depends where you're going to make or potentially risk making a mistake. Are you going to do it in the row reduction, or are you going to do it in the substitution and simplification? So, you know, the best advice is solving linear systems is hard. Choose what works for you. If you like the row reduced, the reduced row echelon form, that's great. If you prefer the back substitution, that's also good. So work out what works for you best. So there's no real easy answer to your question, Tom, because you can make mistakes no matter what. Does that make sense, Tom? Yeah. Sometimes the questions will also tell you what to do. If they want a reduced row echelon form, then they'll say it. Okay. All right. Let's have a look at a slightly more challenging one. So let me go back to my PDF. All right. Question 24. For the following linear systems, find the condition on the vector B that ensure the system has a solution. Okay? And I think what they mean here, they mean it has at least one solution. So let's actually have a look here. So part A, 3 equations, 3 unknowns, and B1, B2, B3, well, we don't know what they are. Okay, so let's write this in a matrix form, and we can do some analysis. Okay, so this is 24. So consider, please, let's consider the following linear system. All right, so this is the augmented matrix. Now, it looks like the one that we just did, but there is something different about it. So some of the row operations are the same, but it's not exactly the same. Okay, if we compare with the previous question, you can see, well, it kind of looks the same, but there's a difference. Yeah. So that entry is different. Okay. So what I would do again with this one is simplify the first row. So some of these are similar kinds of operations. Okay. And what I would do now is the same as before. Row 2 becomes row 2 minus 3 row 1. And row 3 is going to become row 3 plus 2 row 1. So we're going to get a similar sequence of steps here. All right, so that's going to become 0, that's going to become 0. There's a 0 here, so they're not going to change. And again, we've got -2 plus 6 here. So that'll be 4 and 0 minus 4. So looking very similar to the previous question so far. Okay. So now if you look at these ones on the left-hand side, this is a multiple of this. So our next row operation will be something like row 3. So now we're concentrating on that submatrix. That's our pivot. We want to make this 0. So row 3 will become row 3 plus row 2. And you can see that's going to disappear and that's going to disappear. So it's a bit different now to the previous question. Okay, so this plus this. So we're going to get the same entry as we had before, just now we have a 0 here. Okay. All right, so now we've finished our analysis. This is in row echelon form. So let's look. There's leading entry for row 1. There's leading entry for row 2. Row 3, depending on what the value of this is, this could be a leading entry. And this has nothing. So this is a non-leading column. Okay. So who can tell me, when will this system have solutions? And will there be one solution? Let's start with an easier question. If this is non-zero, yeah, Liz, you're on the case. Good typing. If this is 0, then this is just a whole bunch of zeros at the bottom, right? Yeah. And if this is non-zero, then you've got 0x1 plus 0x3 plus 0x2, whatever, equals something that's non-zero. So that's a problem. That's a problem. If this isn't 0, then we've broken mathematics. We've broken it. So let's make some conclusions about that. And we can, so if B3 plus B2 minus a half B1 is 0, then solutions exist. Okay? Then solutions exist. And because we have a left-hand column that's non-leading, you would expect that there will be an infinite number of solutions, right? There won't just be one solution, like in the previous question. Okay, so in the previous question, every one of these left-hand columns was leading. Not in this one. This would be your parameter. You'd sub it in and do all that. Okay? And if this is non-zero, then no solutions exist. So this kind of shows you how the right-hand side of your linear system influences the problem in a huge way. Okay? In a huge way. So for example, if B1, B2, B3 were all 0, then you know that the original system has at least one solution, right? But if B1 was 0, B2 was -1, and B3 was +1, this linear system has no solutions. Okay? All right, thanks for coming in, everybody. All right, let's do one more question. All right, and it's one of these geometric questions. Okay, so let me just do some stuff in GeoGebra in the background, but I'll just share the PDF with you. So you should be able to see that. I'm looking at question 26 here. So let me just bring up GeoGebra. And I'm just going to code up some pictures here. So just give me a second. So just have a look at this question and see how you might do it. I'll just do this stuff in the background. Okay. All right. So yeah. Okay. So I can move over now to GeoGebra. I should be able to share that with you. And so here I put some 3 points in three-dimensional space, and I'm just putting these vectors in. Join these. Okay, and let me just see. Just hang on a second. I'm just going to go back to my question. I'm going to put another point in. Okay, so I can go back now. Okay, so you can see here I've got a point A, a vector V, and a vector U, and the plane in question, it contains A and is parallel to the vectors U and V. So let me see if I can do this. So I'm going to do A, U, V. There we go. Okay, so that is how I've taken that and used GeoGebra to form the geometric plane. Now P is the point to see whether we asked, does P lie on the plane? Well, you can see from the picture, yes, it does. Okay, so we know from GeoGebra that it actually does lie on the plane. How do we do this using matrices? Well, I'm glad you asked. So what we would do then to do this using matrices, you would take this and replace the vector x with this. And then you've got 3 equations and 2 unknowns. The unknowns are the value of lambda1 and lambda2. Okay, so let me write some of this out, and we can try to solve it together. All right, so this is 26. So we are considering the following expression. We want to know, does this problem have a solution? Okay, so are there values of lambda 1 and lambda 2 that makes this equation hold, that makes this equation true? Okay, so what we need to do is get from this form to some sort of augmented matrix form. Okay, so what I'm going to do, and sometimes students ask me a lot about this, I'm going to take this vector to the other side and these vectors to the other side of the equation. The only real reason I want to do that is because you get this -1 turns into a +1 when I move it to the other side of the equation. Okay, so if I do that, then I get this. Okay, so it'll be this vector minus this vector. So 2 minus -3, 5, -1 minus 6 gives you -7. Okay, now you don't have to do that, right? So let's now write these columns as columns of your vector, your matrix, sorry. Okay. Okay, so there you have it. Now all you need to do is row reduce this this matrix. Okay, so can anyone suggest what we might do first? Tom, good question. What happened to the lambdas? The lambdas are your variables now. So the lambdas have disappeared. These are all about the coefficients, right? Just like in the previous questions, there's no x1, x2, x3 here. They're all disappeared, right? They're hanging out. So we're not interested in the lambda 1s and the lambda 2s in here. We're interested in their coefficients. Does that make sense, Tom? So, you know, just like you have, so this is a bit hard to see, but see how we've got a linear system there? x1, x2, x3. There's no x1s, x2s, and x3s there. We don't need them in here, right? We sort of know that that's the x1 column, that's the x2 column, that's the x3 column. Now, are you talking about this matrix here, Tom? Because there's no x1s, x2, x3s here. What we've done is we've taken x1, x2, x3 and said x1 equals -3, x2 equals 3, x3 equals 6. We've actually chosen values for x1, x2, and x3. And we want to say, is there a corresponding value of lambda 1 and lambda 2 that makes this thing true? Okay, that's kind of what we're asking here. Yeah, so we've actually put in specific values of x1, x2, and x3. Okay, so let's row reduce this. So the first thing I would do is actually go with row 2. I would say row 2 can become -1/2 times row 2. So we're simplifying that one by taking out the common factor. Okay, and so, yeah, thanks, Nisa. And so now this is going to be your pivot entry, and I want to annihilate everything underneath that to a 0. So that you want that to be 0, you want that to be 0. So row 2 is going to become row 2 minus row 1. Row 3 is going to become row 3 plus 4 times row 1. Yep. So now what are we going to get? Well, row 1 is not going to change. That's going to become 0. That's going to become 0. So 1 minus negative 3. 1 minus 5. That's 0. That plus that is going to be negative 4. That plus that. Oh, hang on. Sorry. Let me fix that up. That plus 4 times that, it's going to be negative 13. See how easy it is to make a mistake? That plus 4 times that, so it's going to be negative 13 plus 20. Okay, so I just saved it there. Whew. Okay. So now you can see, well, row 2 and row 3 are a multiple of each other. So we can simplify that straight away if you want, or you can just go like this. But you don't have to do this step, but I'm going to do it. And you can see, well, row 2 and row 3 are exactly the same. So it's very easy to finish this off now. Row 3, it's going to be row 3 minus row 2. Okay, so the question now is, are there lambda 1 and lambda 2 that satisfy this equation? Who can tell me in the chat? Is it yes or no? Tom says yes. Cynthia also says yes. Well, you're absolutely right, Tom and Cynthia. You can see here, this is like your lambda 1 column, this is your lambda 2 column. You can see lambda 2 is going to be negative 1, and then you can get lambda 1 from row 1. Okay, again, all the left-hand columns are leading, and the right-hand column is not leading. So the system must have a unique solution. So all the left-hand columns are leading. They're called leading columns. And the right-hand column is non-leading. What that says is the system has a unique solution. Hence, the linear system has a unique solution. Thus, our point P must lie on the plane. That's it. Yeah, Tom, you're already thinking about next term. Do you recommend in-person or online? Tom, they're both good. It depends what you prefer. They'll both be very good. So if you want the face-to-face, that's an option, and that's an option for you, go for it. If you want the online, go for it. Some people don't have the choice. Yeah, so that's week 9. Thanks for listening. I'll see you in week 10. It's the last one. It's the last tutorial next week. I can't believe it. It's very, very sad. I think I've got something in my eye. But thank you very much. And we will see you next week. Bye, everyone.